negative charge. Hello and welcome to this video of Circuit Analysis course unit, in which we will introduce electrical variables that we will come across again and again and again in this particular course unit. So we will firstly look at electric potential or voltage, then introduce electrical current, and then look at power and energy. So here we have a large amount of negative charge electrons at the bottom of this diagram. And these electrical charges create electric field. So if we find that there is a positive charge, then this positive charge is attracted to the negative charges, a bit like a body floating in space somewhat above the Earth's surface being attracted to the Earth by the gravitational pull. As we move this electrical charge, positive charge, away from the negative charges through the electrical field, we are doing work. This is similar to the work you would be doing as you're lifting a ball away from the surface of the Earth. And as we are moving this positive charge further and further away from the negative charges, we are increasing the amount of energy stored in the electrical field. So moving a charge in this electrical field involves work, and this work is related to both the amount of charge as well as the strength of the field, as described by the potential. So if we are doing work, if we're using energy to move charge in the electric field, then the potential or voltage of the charge is raised. Conversely, if energy is being released from the movement of charge in the electric field, then the potential or voltage of the charge is lowered. So here we have an example where we say that we have a charge of 10 coulombs, and that charge of 10 coulombs is moved such that its potential has been raised by 5 volts. So the question is, how much energy is being used? So we use the equation given here, dE equal to Q times dV. So we look at what is the amount of charge that we have. Well, we have charge of 10 coulombs, and we are moving it from voltage, say V1, to a voltage V1 plus 5 volts. So now we essentially integrate the expression for the charge as we move through the electrical field, but because the charge is constant and independent of the voltage, we simply multiply the voltage by the charge between V1 plus 5 and V1. So we get 10 coulombs multiplied by V1 plus 5 minus 10 coulombs multiplied by V1. And so the answer is 50 joules. So in this particular example, because the charge is constant and doesn't change with respect to voltage, we could have calculated energy simply by multiplying charge with the voltage. So now we look at another very important variable, which is electrical current. So what is electrical current? Well, it's simply a rate of charge flow, dq by dt. What's the rate of charge flow in a given time frame? So here we will notice that the charges are moving from left to right, and we're essentially asking how many of these little bubbles disappear or reappear from the screen in a given length of time. And that is essentially how we define electrical current. So let us look at this example where we say we have electrical current equal to 2 amperes and is flowing through a conductor. How much charge passes through this conductor over a period of 2 minutes? So we are given a current, we're given a length of time during which this current flows through a conductor, and the question is how much charge passes through this conductor over a period of 2 minutes. So we simply re-express the previous equations. So instead of having I equal to dq by dt, now we have dq is equal to I times dt. So I is the current, and we integrate the current over time from t equal to start up to t equal end. So let's say the start is t equal to 0 and end is t equal to 120 seconds. So we use SI unit for time. And the current is 2 amps. It is constant. It is not changing with time. It's time independent, time invariant. So we simply get a charge by multiplying current with time, and the answer is 240 coulombs. So if we have 2 amperes flowing through a conductor for 2 minutes, then we have 240 coulombs of charge that has passed through a conductor. In addition to voltage and current, we will very often be concerned with power associated with particular circuit elements. So what is a power? Well, in general, power is the rate at which the energy is expanded or absorbed, and it's shown in this equation here, P equal to dE by dt. Now, in the context of electrical systems, we can actually expand dE by dt using essentially a chain product rule. So we've got dE by dq multiplied by dq by dt. And then we ask ourselves, what is dE by dq and what is dq by dt? Well, dE by dq turns out to be voltage, and dq by dt turns out to be current. So the power is equal to voltage across a given component multiplied by the current flowing through that component. And the very important point to remember is that this equation for power applies to any circuit element. We may come across some other equations that may only apply to resistors, that may only apply to inductors or capacitors or voltage sources or current sources, but as far as this particular expression is concerned, it applies to any circuit element.